okay? So you got second y expect x plus y equals tangent of x. The left-hand side is easy, right? It's constant coefficients. But what's the problem over here? Okay, condition 2 doesn't hold. Take tangent x and start differentiating, it just keeps going on and on. There's not a finite family for tangent x. So I can't use the method of variation of parameters. Sorry, I can't use the method of term coefficients. But the theory that we learned still holds, right? It's a linear, non-homogeneous equation. And when we did the theory of nonlinear equations, we did the theory of inhomogeneous linear equations, we said the coefficients could be variable. It could be like a 5x in there or something like that. And the right-hand side could be anything, right? So therefore, superposition still holds over here. The general solution is the sum of what? The homogeneous solution, which is easy in this case, and the particular. The particular is the one that we have to, is new now, right? Because it doesn't have a finite family. So again, homogeneous solution. Okay, that's easy. It's y double prime plus y equals 0. We did that one, I think, just a couple minutes ago. The characteristic equation is r squared plus 1 equals 0, plus or minus psi. So you get sines and cosines, right? So I'll write down y sub c of x, the complementary solution, is equal to some arbitrary constant times the sine of x plus an arbitrary constant times cosine x. That's, nothing new. But now, what do I have, right? If I put y sub p is equal to a tangent x, it's not going to work, okay? I've tried to crank out the family of tangent, it just keeps going on and on and on, okay? Problem, right-hand side does not have a finite family, okay? So what does the method of variation of parameters do? What it does is what's called variation of parameters. Notice that in the homogeneous solution, C1 and C2 are constants. What variation of parameters does now, it says, let me take those C1 and C2 and replace them by functions of x to be determined. That's why it's called variation of parameters, right? C1 and C2 are constants of parameters. Variation of parameters, I'm going to replace C1 by some function, say U1 of x, replace C2 by a function U2 of x. And you may rightly say at this point, who says that that's going to lead to anything? I'm going to show you, in this case it does, and I'm going to show you that in general it works, okay? So, what we do now is the following. Assume, at this point, y sub p of x, okay, equals u1 of x, which I don't know, right, times the sine of x, plus another function, u2 of x, which I don't know at this point, times cosine x. Okay? Well, let's try it out. Let's crank out yp prime, yp double prime, put it in, and see actually if we can solve for u1 and u2, so that that's a solution. And again, remember the great thing about the theory of differential equations that we proved is that I don't care, I don't need the most general particular solution. I need a particular solution. That's why it's called y sub p, a particular solution. Okay? Because once I have the particular, I just add it on to yc, and I have the most general solution. Okay. Now, one thing, okay, which the book doesn't really do a good job of at this point, and I want to point out to you, is that how many conditions, so to speak, do I have here? I just have one. Y of x has to be a solution of this differential equation, right? Usually, even in nonlinear equations, the number of unknowns should match the number of equations. Okay, so I have one condition here that I can satisfy, namely, y satisfies that, or yp satisfies that in this case. And I have two unknowns, u1 and u2. Okay? I got too many unknowns. So what I'm going to do is, out of convenience, eliminate a certain combination of u1 and u2, which you'll see in a second, to make our job easier, and also allow us to solve for u1 and u2. Okay? When you have basically just one equation and two unknowns, you can't find a general solution to that. But again, remember, as long as I come up with a particular solution, I don't care. So let's make it as simple as possible. Okay? So, first step. What's yp prime of x? Just using the product rule. I'm going to have u1 prime of x, right, times the sine of x, right, plus u1 cos x, right, using the product rule on that, u1 prime sine plus u1 cos x, And then for this guy, of course, I get the same thing, u2 prime times cos x plus u2 derivative cosine is a minus, so it's minus u2 sine x. Okay. Now you can see if I keep u1, u2 like that, and I do yp double prime, oh, it's going to become very messy. Okay. Plus, I know that I have to put in another condition anyway. Now, what would be the simplest thing to do? The simplest thing to do is, if I can get rid of the u1 prime to the u2 prime, then when I differentiate, I won't get u1 double prime and u2 double primes, right? I won't have first order equations, like reduction of order in a way. So here's the constraint that we're going to impose. Okay? And again, the reason I can do this is because I have only one condition to satisfy, namely this, and I have two unknowns, u1 and u2. So I'm going to add a constraint that makes my job easier. And the constraint will be the following. I want to get rid of those primes. Sine x, u1 prime of x, plus cosine x, u2 prime of x. Let's make that identically 0. Okay? Everyone understands the reason why I can do that? Because I'm free to impose any condition at this point. But again, who says that doing this stuff just, because it makes it easy for me doesn't mean mathematics is going to allow me to do it, right? But I'm going to show you that's going to work out at the end, and then we'll do it in general. Okay? But the important thing to realize over here is that we have two unknowns, u1 and u2, only one equation. So therefore, if I have any hope of getting a solution for u1 and u2, I have to write down a constraint amongst them. And the simplest thing is to do this, so when I differentiate, those guys go out, right? So now what happens, okay? Because I made the constraint sine x u1 prime plus cos x u2 prime equals 0, this term goes out, and that term goes out, right? And now my yp prime is just u1 cos minus u2 sine. And then we use the product rule on that to get the second derivative. Okay. So with that constraint, Ash, I want to put a little box around that constraint because we're going to have to come back to it later on. Okay. Okay. That's what we imposed. Okay. What's yp double prime of x? Okay. Use the product rule. I'm going to have a u1 prime of x times a cosine, right? Minus u1 sine. Right? Everybody got that? u1 prime cosine minus u1 sine. And differentiating this, I get a minus u2 prime times sine of x minus u2 cos x. Okay, check that again. u1 prime cosine minus u1 sine minus u2 prime sine minus u2 cosine of x. Okay. Now let's just do yp, let's plug into the left-hand side, see what happens. So what's L operating on y sub p? Yp double prime, which I got right over there. So I've got the derivative of u1 with respect to x times the cosine of x minus u1 sine x minus u2 prime sine minus u2 prime sine minus u2 cosine. Okay, so that's basically the yp double prime plus yp. Okay, where's my yp? Right over there. u1 sine plus u2 cosine. What's really interesting now is you notice everything in u1, u2 cancels, right? Here I got a minus u1 sine plus a u1 sine, u2 cosine, minus u2 cosine. Okay? So, L operating on y sub p now simplifies to cosine of x, the derivative of u1 with respect to x, minus the sine of x times the derivative of u2 with respect to x. But we know what L operator on yp is. That's going to be equal to the tangent of x. Okay? So that'll be my second equation over here. Okay? So what happens now? You know, let's look at these two equations and put them together. I've got one linear equation on u1 prime, u2 prime, another one on u1 prime, u2 prime. And I can solve them by Cramer's rule, or if you don't know linear algebra, you can just do it by elimination. Okay? So what we found is the following. We found out that, I'm going to write this in matrix form again. Again, I realize people have had linear algebra, but I want to show you how the Wronskian occurs over here. Okay? Again, if you haven't had linear algebra, don't worry, I'm not going to hold you responsible. But let's just write the first equation in a matrix vector form. I've got sine of x times u1 prime, and then a cosine of x, u2 prime, from the first equation. In this equation, I've got cosine of x times a u1 prime, a minus sine x. That multiplies the vector u1 prime, u2 prime. And of course, the first equation is the constraint, so it's 0. And here I've got the right-hand side, sorry, which is tangent of x. Okay? What's interesting over here is, what's in the first row of this matrix? I've got y1, y2, right? And you notice how the second row is just the derivative of the first row? That's the Wronskian, if you look back. The Wronskian basically was constructed so that the first row were all the homogeneous solutions, and the second row were the derivatives of those. And here we have two equations, two unknowns, and we're going to solve those for u1 prime, u2 prime. Hopefully we can integrate and we'll get u1 and u2. But what's interesting about this technique is how the u1 and u2 dropped out, and we just got two equations and two unknowns, just u1 prime and u2 prime. Okay? So let me go back now to not using linear algebra, and we'll just try to solve those two for the two unknowns. Okay, this is nothing more than two equations and two unknowns. Okay? Let me write down the first equation again. So I have sine of x times the derivative of u1 with respect to x. I'm just copying this thing again. Cos x u2 prime. That was our constraint, right, that we imposed. Sine x u1 prime plus cos x u2 prime equals 0. And the second equation is cosine x, the derivative of u1 with respect to x. And then there's a minus sine x u2 prime. And that guy has a tangent x on the right. Just tangent x, right? Our unknowns are going to be u1 prime, u2 prime, right? And then if I can integrate them, I'll have u1 and u2, and then I'll have my particular solution, right? u1 sine plus u2 cosine. Okay. So make believe we're in two equations, two unknowns. Okay, let's see. How about the following? Let's get rid of this guy. Here we have a cosine, here's a sine. I'm going to multiply that guy by sine of x, and multiply that guy by cos x, and then add. Ever see what's going to happen over here? In the first equation, I'll have cosine sine u2 prime minus sine cosine u2 prime. That'll go to 0. Okay? So, now what happens in this thing, I'm going to do a little bit in my head. I'm going to get sine squared u1 prime plus cos squared u1 prime. Hopefully you remember sine squared plus cos squared is 1. So this comes out to nothing more than the derivative of u1 with respect to x. These two guys cancel, okay? What happens on the right-hand side? I take 0 multiplied by sine x, that's still 0, but don't forget to do tangent times cosine. Tangent is what? Sine over cosine, so that just becomes sine of x. Okay? This is something you've done already, it's all symbols instead of like, numbers, right? It's solving two equations and two unknowns. Okay? Now, one thing which is important that I want you to pay careful attention to, I'm going to integrate this now. And you say to yourself, do I need an arbitrary constant? And I'm going to tell you no, and let me tell you why. Okay? Because you have the homogeneous solution already, right? It's a linear combination of sine and cosine. And we know at the end we're going to say the solution is yc plus yp, right? So you have the homogeneous solution, sine, cosine, okay? And then you assumed a particular solution, where was that? Here, u1 sine plus u2 cosine. Suppose when I integrate that equation right over there, I integrate u1, which is b minus cosine, and plus an arbitrary constant. Well, now u1 will have an arbitrary constant multiplying sine, but that's already in the homogeneous solution, so you don't need it. Okay? You're accounting for it twice. So when you get to this point, it's very easy. You just integrate this thing. You get u1 of x equals minus cosine of x. Okay? That's all you need. Because if you added a constant to u1, when you multiply it over here to get yp, you'd have a multiple of sine x, but you have that already over there. Okay. And now let's get the derivative of u2 with respect to x. I guess I'll use the first equation, right? For the first equation, I get cos x u2 prime, right, equals minus sine x u1 prime. Right? Cos x u2 prime equals minus sine x u1 prime, but u1 prime is sine. So it's just minus sine squared. Okay? So the derivative of u2 with respect to x is minus sine squared x divided by the cosine of x. Okay? Okay, I guess I'm going to use an identity over here. Everybody remembers the identity sine squared plus cos squared equals 1. So sine squared is 1 minus cos squared. I write that as cos squared x, take away 1. That's what minus sine squared is, right? Divided by cosine of x. Okay, and again, I want to give you integrals. If as difficult as this on an exam, I give you what the antiderivative. Cos squared over cosine is just cosine of x. Okay, everybody knows how to integrate that. Then I get minus 1 over cosine, which is minus the secant of x. Okay, and now I integrate that, and you take out, you don't need a calculus book for this one, right? We all know that that's sine of x. And if you look in your calculus book or a table of integrals, you'll find that the integral of secant is the log of secant plus tangent to base e, of course. Okay, so now I got u1, I got u2. Now I can write down my particular solution for this problem. So, y sub b of x, just look at what you did, okay? u1 sine, so it's minus sine cosine, right?